Okay, folks, let's go ahead and let's get started. A couple things about the AP exam before we continue on with the discussion of hybridization and finish up the discussion of the localized electron model. And that is make sure then that on the day of the exam, for our exam, you show up on time for our time. Um, if you don't show up for that exam, you're going to be automatically shifted over to the retesting date in June. If you choose not to take the exam, if you decide at the end not to take the exam, make sure you contact the office about getting a refund for your fee. Okay, so make sure you take that into consideration. However, I would suggest that you take the exam. The word on the street is that they will be, or they may be, grading the exams more leniently, and so you have a better chance of scoring a passing grade of 3 or more. You have a better chance of doing that. There's obviously no guarantee about that, but the word on the street is that they will be grading more leniently. And so do consider taking the AP exam. I think we've already talked about the format. It's a free response exam, 45 minutes. You can use your phone. I'm not quite sure about any lockdown browsers. I'll check up on that for you. But you can use your phone and to take the exam. That way, then you can take a picture. If you feel more comfortable writing things out, you can take a picture of it and then submit it that way. Okay. Next week they will be posting for you a student guide for the AP exam. So take a look on the AP web page for the AP exam for that, and also to make sure then that folks that you are registered. So don't assume that you are registered. Make sure you go on to the AP website there that we went over, that I gave to you in class when we were still together. Make sure you take a look at that. Go to the website and make sure that you are registered and ready to go. Okay. I will check also, but the last time I checked, I think everybody except for one person is going to be taking the exam. So I think everyone's good to go. But like I said, make sure you also check. Okay. Um, and that's pretty much it. That's kind of the new information that I've been getting, that I've gotten today, yesterday. And so if anything else comes up, I will pass it on to you. Okay. So I think the thing is, the take-home message for that then is to make sure that you go ahead and take the exam, try it. If nothing else, it's only 45 minutes of your time rather than the 3 hours that would typically be required of you. So invest that 45 minutes, do your best with it, and like you said, the word on the street so far is that they may be grading it more leniently, so you stand a better chance of getting a passing grade, a 3, 4, or 5 on that exam. Okay, so make sure you review, make sure you continue to review for the AP exam. Come by and see me if you have any questions about the preparation for your AP exam, and then I can help you with that. Okay. Okay, let's go ahead and let's pick up where we left off with yesterday. And we were talking about describing the bonds and the interactions of the atoms in a molecule. Okay, so for a molecule, you have to be able to identify the bonding type, okay, single bond, double bond, or triple bond. You should be able to describe that from the hybridization of the atoms in the molecule itself. Make sure you're able to describe the hybridization of each one of those atoms. Then make sure you can describe then the bonding interactions. How do those bonds form? How do the orbitals overlap in order to form these bonds? Okay, so we were able to kind of generalize and say then that with single bonds, for the most part, you're going to get the sigma bonding interaction. We have the linear interaction where the orbitals line up along a single line. You then have the pi bonding interactions where you have the two orbitals line up side by side. We said then that you only see the pi bonding interactions in double and triple bonds. So with the double bond, you can have a single sigma bond and a pi bond together to form that double bond. With the triple bond, then you're going to have a sigma bond and two pi bonding interactions in order to form that triple bond. Okay. And the only way you're going to be able to do that is you need to be able to take the formula. So, for example, here with sulfur dioxide, and so this is the problem we left off with yesterday. Sulfur dioxide, you need to be able to draw the Lewis dot structure first. Okay, so draw the Lewis dot structure. From there, then you can go ahead and describe the hybridization. Once you have the hybridization, you should be able to describe the type of bonds that form. And once you have the pictures drawn, you should be able to identify then the bonding interactions that form from that. Okay, so this is where we left off with yesterday. So we were able to draw the Lewis dot structure for sulfur dioxide as such. And we see then that there will be, for each one of these atoms here, there is a 3 electron domains, and so therefore each one of these atoms be sp2 hybridized. If we draw it this way is here, okay? And so if you were to do the formal charges, and I do highly suggest that you go through and you calculate for the formal charges that we worked with in the last chapter, you would be able to calculate then the formal charge for each one of these atoms will be 0 in each case then. So this represents then the most stable form of sulfur, or the most acceptable form of sulfur dioxide. Now, with that said, though, there is an alternate form which I want to be able to draw. I want to draw for you. There's an alternate form that will allow us then. Let's take a look at this alternate form there. That will allow us then to better understand how these interactions occur. And this alternate form then will involve a double bond, or one oxygen in the sulfur, and a single bond for the second oxygen and the sulfur. In this case, then, if you notice, and in this case, then, each atom has their octet. Each atom will have their octet. And with that said, then, if you see this, then, let's go ahead and talk about the hybridization of each one of these atoms. So with sulfur here, you have 3 electron domains, trigonal planar geometry. This is going to be sp2 hybridized. Same thing holds true for this double bonded oxygen. Nothing changes there. This is going to be sp2 hybridized. However, with this oxygen here, then you have 4 electron domains, which assumes then a tetrahedral configuration. This oxygen then is going to be sp3 hybridized. Now, this structure here is also a valid structure. Make sure you take a look at this. And based on, if we ignore the formal charges, this looks like the better structure than we have here. Because here then, every atom has their octet. Every atom has the 8 electrons that makes it stable. Okay? But remember, with sulfur and the larger atoms, the period 3 atoms and up, they can accommodate more than 8 electrons. They can expand their octet to accommodate more than 8 electrons. Okay? And so with that said, then let's check formal charges here really quickly. If you were to do the formal charges on these, and again, please make sure you come by and you see me if you have questions about this, you're going to get then a -1 here for oxygen. You're going to get a +1 here for sulfur, and a double bonded oxygen will always give you 0. So there is the formal charge for this particular molecule here, which doesn't really make this favorable. Remember, that's okay. Oxygen's more electronegative, so it can handle the negative formal charge here. But with that said, then the sulfur, again, we want to avoid positive formal charges if we can. If we do have a positive formal charge, if it falls on the less electronegative atom, then that's fine as well. But the ideal structure then should have all atoms having 0 formal charge. Okay, so here you have then a sulfur with a positive, and sulfur is a somewhat electronegative. It's an electronegative atom. It's right underneath oxygen. So this isn't a good thing here. Okay. All right. So with that said, then, if this is the structure, we can go ahead then and we can also talk about the bonding interactions here. Okay. So here then we would have a sigma bonding interaction. We have one sigma bonding interaction there. So sigma bonding. Okay. And for the double bond here, one of these will be a pi bonding interaction. And the other one would be a sigma bonding interaction. So for this structure of sulfur dioxide, you can have 2 sigma bonding interactions and 1 pi bonding interaction. Okay? And for this structure here, then you can see that you can have 2 sigma bonding interactions and 2 pi bonding interactions. Okay? All right, so this should then be the more valid of the 2 structures. Okay, but let's do a quick analysis here. And again, like I told you, you do not need to draw the next structure, but I want to be able to analyze this for us. Okay, and let's go ahead and take a look at this. Okay, so using our little bubbles here, okay, it hopefully will help you kind of see this. So sulfur then is sp2. We said it's sp2 hybridized with its 3 sp2 hybrid orbitals, and so make sure you keep this in mind here. What we have here then is an sp2 hybrid orbitals, and you have 3 of them right there. Those are the hybridized orbitals made of 1 s and 1 p. And 2 p's hybridized together. So you end up with 3 sp2 hybrid orbitals. Same thing holds true then for the oxygen. Okay? Oxygen's going to have 3 sp2 hybrid orbitals as well. Each oxygen will have its 2. Okay? It's 3, I'm sorry. So you have sp2 hybrid orbitals here. You have sp, so let's go ahead and label all the sp2 hybrid orbitals. You have sp2, 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 sp2. This is sp2, and there are your all 3 of the sp2 hybrid orbitals for each one of the atoms. And I'm sorry, one sp2 here. All right, so you can clearly see then that one bond that forms here, this one's going to be a sigma bonding interaction. This is going to be a sigma bonding interaction. It follows along the line, so you have a sigma bonding interaction here. Okay, and you also see then that there's another sigma bonding interaction here. So you have a sigma bonding interaction as well there. Now, how does that occur? Well, let's fill in the electrons. Okay, all right. So each atom here has to have 6. Sulfur and oxygen have 6 valence electrons, and you can imagine then each one of these lone pairs, a lone pair will fall into one of those hybrid orbitals, and you'll see it here and here as well, because you have a lone pair here. And so I want to be able to draw this structure here. Okay, and let's go ahead and draw this structure. I'm sorry, let me go ahead and draw for you this structure first. Okay, where you have all atoms with their octet, because I think it's a little bit easier to see how this works out. So let's draw this structure first, and then we'll talk about the structure that fits formal charges better. Okay. All right. So you have, then you can imagine these 2 electrons here. There are the 2 valence electrons here. So you have then, and I'm sorry, I overdid it with the electrons here. Let's erase these here. Okay. All right. So you can imagine these 2 lone pairs. There's this one, and there's lone pair here. Okay. And so with that said, then you can imagine there's a electron here, okay, and electron here. Okay. So right now, then we've counted for 1, 2, 3 of the sulfur 6, and we have 1, 2, 3, 4, 5 of the oxygen electrons. Okay. And we haven't yet dealt with the electrons for this oxygen yet. So with that said, then you can imagine there, with this overlap here, there has to be an electron here for sulfur. There's an electron there, or else this bond doesn't form. But let's consider what we have here in just a moment. Okay. All right. So we have then 1, 2, 3, 4. We have 2 more missing here. We have 1 more missing here, and we are dealing with the 6 electrons. We still don't have that yet. Okay. So let's go ahead and let's take a look at how this bond forms. Okay. This bond forms, and remember, this oxygen here has 1 more electron that we have to count for. The orbital here is already taken up. These 2 orbitals are already taken up here. Okay, so where does the last electron go? Well, remember, there's the unhybridized p orbitals, okay, in each one of these. And so remember, each one of these here, all these atoms lie along a plane. This is a trigonal planar, so you can imagine these p orbitals coming up above the plane of this paper, board here, and below. So these p orbitals here. So this is a p orbital from. So this is a p orbital, unhybridized p orbital for sulfur. This is the unhybridized p orbital for this oxygen, and this is the unhybridized p orbital for the second oxygen. Okay, so there are the unhybridized p orbitals, because remember, with sp2 hybridized atoms, 2 of the p orbitals are hybridized, 1 is unhybridized, and that's what we have here. And so you can imagine then 1 electron, the last electron for oxygen will fall in right there. Okay, and you can imagine that we have 1, 2, 3, 4. You can imagine a 5th electron going in right there. And so this is a sigma bond. And you can imagine the interaction here between these 2 pi orbitals, p orbitals here, forming a pi bond, pi bonding interaction there. And there is the double bond. There's the double bond between this oxygen and the sulfur there. So this bond here is sigma bond. It falls on the line. We have a sigma bonding interaction here, and there is our pi bonding interaction here between this electron here and this electron here. Okay. All right, so we have the 2 electrons sharing here to form this bond here. There's 2 more electrons here sharing that bond. We've accounted for all 6 electrons for this oxygen here. You got 2, 4, 5, 6. We're done with this oxygen here. Okay. This sulfur right now, we have 1, 2, 3, 4, 5 of the 6. Okay, 5 of the 6. Okay, and in this case here, we have 6 valence electrons total. Okay, so let's imagine what happens here. Okay, this oxygen is, this bond here is going to form from a coordinate covalent bond. Okay, this bond then, remember we talked about the coordinate covalent bonds. There it is. two electrons, there's two electrons in this orbital here, and it will form then this bond right here, this sigma bonding interaction. These two electrons here will flow between both sides of these orbitals here, okay? Which means then this oxygen here will have all of its pairs in those orbitals, okay? So there we have it. We have then electrons. There are the 6 electrons from this oxygen, okay? And so what we've just drawn here is this structure for sulfur dioxide. So how does this structure, which is the more valid structure for sulfur dioxide, come about? Well, we talked about resonance. Remember we talked about resonance, okay? And so you can imagine then what happens is that you have a sigma bond forming here. So what happens then is you can have then a second bond here. These two here, they fall in, or one of these two, they fall in and they form the pi bonding interaction here. Now, technically the pi bonding interaction will be between this p orbital and this p orbital here, okay? But that's where the second of the two bonds form there. Okay, so basically you can imagine that a coordinate covalent bond forming here as well, where the double bond here is formed between these two electrons and these two electrons here. Okay? And so that's how we can go about examining the structure for sulfur dioxide. Now that's quite a bit, and you are not expected to draw these orbitals here. You should be able to explain then the bonding interactions from the Lewis dot structures here. So make sure you're able to do that. What I'll do then is I will also post these notes for you, like I did yesterday. I'll post these notes for you. Please make sure you use them in order to help you kind of better understand how we can characterize these bonds here, and the difference between this structure and this structure here. Okay, so please make sure you study these. Good. All right. Very good. Let's go ahead then. Let me ask you then, let me just go ahead and go through a couple of these with you. I'm just going to give you the answers for them. I asked you to work these out yesterday as well. So for this particular structure here then, for iodine pentachloride, okay, it's going to be a D2sp3 hybridized hybridization for the iodine, the center atom. For each chlorine then, we're going to have the chlorine then. So this hybridization here is going to be for the iodine. So this is for iodine. I would be curious to find out then, what do you think the chlorine's hybridization is going to be? Well, hopefully if you counted the, just real quick in your head, if you count them, each chlorine then is going to be sp3 hybridized because they will each have then 4 electron domains around them. Okay, so each chlorine is sp3 hybridized, each iodine is going to be D2 sp3. The reason for that then is we need six locations for these electrons to go into, okay? Which gives us then each single bond then, you'll have a single bond forming between each iodine and each chlorine. The single bonds then will all be sigma bonded, will enjoy sigma bonding interactions, okay? And so make sure you draw the structure. If you want this structure drawn out, if you want to talk about this, please make sure you come by after school today and see me. So I will be available after school today. I apologize. I forgot about my meeting on Monday and yesterday. So Tuesday and yesterday. So please make sure you come by and get your questions answered at that point. Okay. All right. Let's go ahead then and let's take a look at the next molecule. Okay. This one I actually do want to draw for you. I want to draw for you because this doesn't look quite as apparent. Okay. So let's go ahead then and let's take a look at what we have here. Okay. Okay. So let's draw the Lewis dot structure for krypton difluoride first. Okay, so hopefully you recognize the krypton is the center atom here. Krypton is going to be the center atom. There's going to be a single bond that forms between krypton and fluorine. Make sure you remember why fluorine, because fluorine has to have its octet, and fluorine must always have its octet. Okay? So therefore, only a single bond forms between fluorine and krypton. Okay, which leaves then for us 8 electrons that we have to account for, because each single bond here is going to be 1 electron from krypton, 1 electron from fluorine. That'll form the single bond. We still have 8 electrons to account for, and each electron then will be paired up. Okay, so if you think about this, then if you can consider that we have 1, 2, 3, 4, 5 electron domains for krypton. So for krypton here, we have to account for 5 electron domains. Okay. So those 5 electron domains then gives us an electron geometry. And remember, you got to make sure you remember this, of a trigonal bipyramidal geometry. Okay. So it has to be trigonal bipyramidal, which means then for this, then you have to have 5 locations for these electrons to go. All of them are going to be degenerate. So therefore then, and I'm sorry, with the molecular geometry, if you're curious about that before I go on, this is going to be a linear molecular geometry, which means then if we have a trigonal bipyramidal electron geometry, the hybridization for sulfur then is going to be D, okay, sp3, which will provide us with the 5 that we need. Okay, so the hybridization for krypton then based on our analysis here is going to be dsp3, and hopefully you see then with each fluorine then it's going to be sp3 hybridized for each fluorine. Okay, and then so with that said, then each one of these bonds here, each one of these single bonds then will be sigma bonding, will have sigma bonding interaction, and I think at that point then it becomes a little bit more easy to see. Okay, all right, so with that said then make sure you are able to get that. Okay, let me go ahead and ask. Okay, all right, so what I would like you to do then is I got one more for you to do. Okay, so what I would like to do is I want you to draw. So we did krypton difluoride. I would like you to do krypton tetrafluoride here. So draw the structure, draw the Lewis dot structure for the carbon krypton tetrafluoride on your paper. Okay, and make sure you submit that after the lecture today, and practice that, because this will be it for it. This will be it for us. Okay, what I'd like to do tomorrow then is I want to start the discussion on molecular orbitals. Okay, and so please preview that discussion in your book. And then I want to round out this chapter by talking about photoelectron spectroscopy. And then I would like to get started on discussion of Beer's law to try to finish out what you'll need to know for the AP exam. Okay. All right, so with that said, then please try this, okay, and draw it on your paper, and then I will see you folks tomorrow. Okay, have a good day, folks.